Okay, so we're going to continue our study of the one-dimensional Poisson equation. This is what we have here, but notice we've added a transport term, and we're going to see what happens when we add the transport term. Obviously, the matrix is going to look a little bit different, but what might happen is that the matrix is going to have different properties. It might break some of the nice properties that the matrix that we had when b is equal to 0. So I have the two different approximation schemes. This is just the standard central second order, the standard central second order derivative approximation that we used in the previous video, and this is the central first derivative approximation that we derived 2 videos ago. So how does this work on the grid? Well, again, let me just remind you what the setup is. We have an interval from 0 to 1. We have an interval from 0 to 1. We're going to divide it into, there's n plus 1 different points. This is x0, and this is xn. And then we're going to set h to be equal to 1 divided by n. So the length of these intervals is equal to h. And I don't know how many intervals I drew up there, but I just want to imagine, I want you to imagine that this is a generic number of intervals. It could be 5, 7, 10,000, whatever it is. And we're going to look at this generic point right here. This is just going to be called xk. And now if we move this approximation to the grid, this mirrors what we did in the previous video, then at each point xk, we're going to have the equation, the approximate equation on the grid becomes the following. We're going to have our second derivative approximation. So we're going to have uk plus 1 minus 2 uk plus uk minus 1 divided by h squared. And I just want to say one thing that I should have mentioned in the previous video that I forgot to mention. I'm going to do it now. We can schematicize this different scheme in the following way. I can write a minus 2 here, a 1 here, and a 1 here, and we usually kind of like write it as a graph like this. Okay? This is called a 3-point stencil, or it's called the 3-point stencil here. And it just means in the difference approximation scheme, we're going to take minus 2 here and 1 there. So the 1 refers to the coefficients that are there, and the minus 2 refers to the coefficient there. When we look at higher dimensions, we'll have other stencils as well. Now, I didn't mention it explicitly, but I'm assuming for now that b is constant. So now we're going to have plus b, to try to write it in this same format over here, b over 2, and then we're going to have u k plus 1 minus uk minus 1 divided by h. And this is going to be equal to f sub k, where as usual f sub k means f of xk. Now, what I first want to do, as I manipulate this, what I first want to do is multiply both sides by h squared. So how's that going to change things? Well, this, I'm going to have an h squared fk but also right here, this was divided by h, so when I multiply it by h squared, it's going to be b times h. And now what I want to do is I want to arrange this in a way that's going to help me see what the corresponding matrix is. And remember, we went over in the previous video that the in the equation here, the kth row corresponds to the kth equation, and then the kth column, the k minus 1 column, and so on and so forth, corresponds to the coefficient on the corresponding u. Okay, so I'm going to write this in sort of a different order. I'm going to look at all the coefficients on uk minus 1, all the coefficients on uk, and all the coefficients on uk plus 1. Okay, so if I look at the coefficient on uk minus 1, what will I have? Well, I have a minus 1 here, so I'll have a minus 1. And then over here, I'm going to have a minus bh over 2. So it's going to be minus 1 minus bh divided by 2 times u k minus 1. Okay, what about on uk? What is my coefficient going to be? Well, this is the only uk that shows up, so it's going to be plus 2 uk. And then what about my coefficient on uk plus 1? Well, I'm going to have a minus 1 here. I'm going to have a minus 1 here. But notice what I'm going to have over here. I'm going to have a plus bh over 2. And then this is going to be times uk plus 1. And this is equal to h squared times fk. Okay, so then what is a corresponding matrix going to look like? Well, this is the kth equation. So 2 is going to be in the kth equation, 2 is a coefficient on UK. So this means that the diagonal is all going to be 2's. Okay, for the kth equation, this is the coefficient on UK minus 1. So remember the k minus 1 column corresponds to the coefficient on UK minus 1. So this is I'm going to call it the subdiagonal. That is the diagonal below the diagonal. And then what do we have over here? Well, this is the coefficient on UK plus 1. And so this is going to be, remember the entries in column k plus 1 are the coefficients on UK plus 1. And so this is going to be the diagonal above the diagonal. It's going to be called the super diagonal. So I want one observation that is very clear right here. This matrix is no longer going to be symmetric. If b is not equal to 0, these two numbers are not going to be equal to each other. So this is no longer going to be a symmetric matrix. Now it does retain some of the structure that we saw before. It's still tridiagonal, and therefore the sparsity pattern is still going to be, well, not therefore, but it is tridiagonal, and the sparsity pattern is also going to be tridiagonal as well. The sparsity pattern is going to be symmetric, meaning that even though the values of the entries are not the same, if we just look at the sparsity plot, that will give us a symmetric sparsity plot. Now again, it's tridiagonal, so we typically would not use iterative methods here, but it is good to see how things work for one dimension before we see how things work for higher dimensions, which is exactly what's happening here. Because a lot of what we're going to do for higher dimensions is just sort of copying this in some sense. Okay, but there's other more subtle problems that we haven't talked a lot about yet, but that we will talk about when we talk about the convergence of iterative methods. So what are those problems? Well, a sort of backup to a matrix as being symmetric is that it is diagonally dominant in some senses. So what does it mean for a matrix to be diagonally dominant? A matrix is diagonally dominant if for each row the absolute value of the diagonal entry is greater than or equal to the sum of the absolute values of the off-diagonal entries. So in the case when b is equal to 0, these two terms are equal to 0. The absolute value of minus 1 is 1. The absolute value of minus 1 is 1. You add those together, it's 2, and it equals the diagonal entry there, so it's good. On the other hand, if b times h is a very big number, let's say b times h is equal to 50. You have minus 1 minus 50 over 2, so minus 1 minus 25. So this is going to be the absolute value of minus 1 minus 25 is 26. And then over here, we're going to get minus 1 plus 25, so that's 24. So the absolute value of this is 24. The absolute value of that is 26. You add them together, it's definitely bigger than 2. Okay, so if b times h is large in absolute value, then we're no longer going to have this diagonal dominance. The other thing that we want to happen, and again, the importance of this we'll talk about a little bit later, but the other thing that we want to have happen is that we want the diagonal entry to be positive, which, yep, that's going to happen here, and we want the off-diagonal entries to be negative, which is not going to happen if b times h is very large. So what we need to have happen then, for these two properties to exist, for the diagonal dominance and the off-diagonal entries to be negative, we need to have the absolute value of b times h divided by 2. This needs to be less than 1. So for over here, if b times h divided by 2 is less than 1, then this is always going to be a negative number. And similarly over here. So what we need to have happen is the absolute value of b times h over 2 is less than 1. And there's a very important thing that I haven't mentioned yet. This is for this equation right here, where the coefficient on u double prime is 1. If we have an equation where the coefficient is not 1, to be able to do this analysis like I did here, we need to divide through so that the coefficient is equal to 1. So what this tells us then, we're solving this equation numerically. We don't get to pick what b is. in the numerical scheme, the only thing that we have to choose over here is h. And this is going to tell us that h needs to be less than 1 over 2 times the absolute value of b. Now, if the absolute value of b is very big, this might give us a value of h that's too small to use. For whatever reason, maybe it won't converge fast enough. Again, a lot of that, we'll talk more about this when we talk about the convergence of our iterative methods. But in other words, but it just says if b is very big, h might need to be too small. Unless we can come up with a different type of scheme that's not going to have this problem. So unless we can come up with a different type of scheme that's not going to have this problem. And I'm going to discuss that right now. But I have to do so to explain exactly what's going to go on. I need to do it with an additional assumption on b. So the only assumption I'm making on b right now is that it is constant. But I also now, I want to make this assumption just for the purpose of this demonstration that b is greater than 0. So remember, b represents the velocity. So if we're modeling like stuff moving down a river, b represents the velocity of the river. And so if b is positive, it means the river is flowing this way, and so information is flowing from this way to that way. And so what we can do then is, instead of using a center difference scheme, we can use a difference scheme where we subtract from the left. Okay, so we could use a scheme like that. Okay, so what we're going to get in that case is going to be the following. The u double prime, that's going to stay the same. So we're going to have minus uk plus 1 minus 2 uk plus uk minus 1 divided by h. And now we're going to have plus b. And now we need to do a different approximation. So what is the approximation for the first derivative going to look like? Well, we want to use, if this is xk, we want to use this one, and we want to use this one right here. Okay, so what will that approximation look like? Okay, it's going to be uk minus uk minus 1 divided by h, and this is going to be equal to f sub k. Oh, sorry, there's an h squared here. Okay, now what I'm going to do, like I did before, I'm going to go ahead and multiply by h squared. So I have an h here, and then I will have an h squared here, and I'm going to collect terms now. Okay, so what is my term on uk minus 1 going to be? Well, I'm going to have a minus 1. So this is going to be I said the term on uk minus 1, I mean the coefficient on uk minus 1. So I'm going to have a uk minus 1. What about over here? Well, I'm going to have a minus h times b, and then times uk minus 1. Okay, what am I going to have on my uk term? Well, notice what's going to happen here. I'm going to have a minus 2, so I'm going to have a 2, and now I'm going to have a plus hb. Okay, so here's where the advantage comes from, because this is going to correspond to the diagonal. In terms of diagonal dominance, I have now added entries to the diagonal. And then finally, for the uk plus 1, well, I'm just going to have a minus 1 here. All there is. That's the only uk plus 1. So I'm going to have minus 1 times uk plus 1. And this is equal, yeah, this is right, okay. Yes, okay, h squared, I thought I was missing an h somewhere. H squared times fk. Okay, so notice what we've done here is we've added hb. Again, h is positive always, and we're assuming b is positive. So we've added that there. We've subtracted it here. So the absolute value of this, so minus 1 minus hb, the absolute value of this is 1 plus hb. The absolute value of this is 1. So the absolute value of that plus the absolute value of that is equal to 2 plus hb. Not only that, minus 1 is negative, and minus 1 minus HB is also negative. So this has both the diagonal dominance that we want, and it has the property where the off-diagonal entries are negative, and the diagonal entry is positive. Okay, so what is a disadvantage? And notice we don't have to have this requirement where h is less than 1 over 2b for those properties to hold. Okay, so why there has to be some trade-off? Maybe this just is a better method. Well, the trade-off is that this has a linear order of convergence, whereas the method that we talked about before had a quadratic order of convergence. So this method has a linear order of convergence, meaning the error in this approximation here is on the order of h, whereas when we do the central approximation difference, the error is on the order of h squared. Okay, so this works great when b is greater than 0. Well, what if b is less than 0? Okay, so let's do that. What's going to happen if b is less than 0? Maybe you guys can even think about what's going to happen. How are things going to change? Well, now what we're going to do, this corresponds to the river flowing this way, so information is flowing from here to here. So we're going to look at a different approximation scheme where we look that way, moving this way. So we're going to have uk plus 1. We're going to have that, uk plus 1 minus uk. And of course, in the approximation, we divide by h, but then when we multiply by h squared, this is what we get. Okay, so how is this going to look now? What is going to be the coefficient on uk minus 1? Well, it's just going to be this right here. That's the only coefficient on uk minus 1. So we're going to have minus 1 times uk minus 1. Okay, now what about the coefficient on uk? What's the coefficient on uk going to be? Well, we're going to have our minus 2, that's 2. And then over here, we're going to have minus h times b. Okay, don't let the negative fool you or scare you. B is less than 0, so this is, 2 plus that absolute value is what's happening. And then what about on uk plus 1? What's going to happen on uk plus 1? I'm going to have a minus 1 here, and then a minus h times b here, uk plus 1 is equal to h squared times fk. It's plus this. Okay, and so now keeping in mind that hb is negative, minus 1 plus a negative number is always going to be negative, and similar reasoning as before shows that we also have the diagonal dominance. Okay, so this gives us a way, if b is positive, we can use the scheme that we had before, which is called an upwind scheme, or this one, which I guess you could call a downwind scheme, but I've never actually heard anybody call that, I don't think. Anyways, if b is positive or b is negative, we can use a different scheme to do this approximation right here. The upside is that no matter what h is, we're going to have a diagonally dominant matrix where the diagonal entries are positive and the off-diagonal entries are negative. The downside is that the order of approximation is now h instead of h squared. Okay, that's if b is a constant positive number or a constant negative number, something like this is going to work. Also, it would work if b is a variable and b is always positive, or if b is always negative. If b is variable, though, if b can depend on the grid, if b is not a constant, it's a function of x, then what we want to do here is have a different scheme that is going to change depending on what the sign of b is. So we want to have a different scheme that is going to change depending on what the sign of b is. So let me just first, if we look at a centered, in other words, if we look at the centered approximation scheme for if we have a variable b, then the approximation scheme is going to look like this. So let me just write it. The approximation scheme is going to be the following. Assuming I'm going to multiply by h squared, So we're going to have u k plus 1 minus 2 uk plus u k minus 1 plus b of xk, which we're of course going to call bk, times uk plus 1 minus uk minus 1, and this is equal to h squared times fk. This is the symptotic one. Okay, so now what we're going to do is, this is typically called an upwinding scheme, because we're looking, if B is positive, we're looking upwind. I guess if downwinding is included under this as well. So it's going to be the following. We're going to have, the approximation for the second derivative is going to be the same. We're going to have minus uk plus 1 minus 2 uk plus u k minus 1. And then now what we're going to do is the following. We're going to do the following. So we're going to have two options. If bk is greater than 0, we're going to do our upwinding. So if bk is greater than 0, it's going to be plus. Sorry, I forgot about dividing this by 2. Okay, we're going to have uk minus uk minus 1 times bk times h uk plus 1 minus uk, and if bk is less than 0, we're going to do the last one that we just looked at. So we're going to have bk times h. Oh, you know what? I got this one backwards. Sorry. Okay, sorry. uk minus u k minus 1, and then over here, sorry, it's an awkward position. bk times h, uk plus 1 minus uk, and this is going to be equal to h squared times fk, like this. Okay, and so this is going to be, again, if you look at the corresponding matrix, this is going to have the properties that we want it to have. Okay, if we look at each row, we're going to have this diagonal dominance property, and the off diagonals are going to be positive, and the diagonals are going to be negative. Okay, so again, the problem with this scheme here, once again, is going to be that it converges linearly. So the other thing is, if we want still a quadratic converging method, we could still just take h to be small enough. And what we need to have happen then is h needs to be less than the maximum of the minimum of 2 divided by the absolute values of all the bk's. And if this is satisfied, then we'll have the properties that we want to have satisfied as well. And again, for this analysis to work, the coefficient on u double prime needs to be equal to 1. So if the equation we have, the coefficient is 1/10, then we have to multiply all of this by 10, and now our new b is going to be 10 times our old b, and now h has to be even smaller. Okay, and one other thing to say, I'm not going to talk more about it in this video, but of course, the coefficient on u double prime, if that is a function as well, we can either divide by a or have a different approximation scheme. I mean, maybe you can see some of the things that I'll post later for what happens in a case like that. Okay, that is it for this video. So what I've done is I've shown you a approximation scheme for the diffusion equation with transport, and I've also mentioned a couple of numerical issues that could happen if B is big. This is dominated by transport, and then we have to do one of two things: either make h sufficiently small or use a different approximation step.